So in this video I'm going to be showing you how I built my very own induction heater capable of heating up metal until it's red in the face. Stick around because this is a cool one. There's a link in the description to this project on my website. You'll find a detailed schematic, bill of materials and PCB Gerber files, plus extra info related to the build. The design is minimalistic, keeping the component count to a minimum. If you'd like to know more details about the components used, they can be found by clicking the link in the corner of the video. I opted to wind my own inductors for this project. Making an inductor is pretty simple. You'll need a toroid ring and enamelled insulated copper wire. I measured out and cut 1.6 meters of copper wire. To make the inductor, all I needed to do was wind the wire around the toroid. Take your time and try to make each wrap of wire uniform. Make sure to keep the wire tight to the toroid and avoid having large air gaps between the toroid and wire, as this will reduce inductance. When you've nearly run out of wire, you should have between 30 to 32 turns of wire, which would give us about 100 microhenries of inductance. And you'll need to make a total of 2 inductors for this project. Before you attempt to solder the inductors to the PCB, make sure to remove the enamel insulation with sandpaper before soldering. The heat sinks I've chosen to keep the MOSFETs cool are a spring-loaded clip design. First I mark the centre of the heatsink, which I'll use as a reference to align the MOSFET. The heatsink is then held in my vise. Thermal paste is applied to the MOSFET and a screwdriver is used to lever against the clip. Simply slide the MOSFET into position and you're done. Now we can move on to assembling the PCB. If you want to order a PCB for yourself, you'll find the Gerber files on my website. One of the diode footprints was too small, so I had to vertically mount the diode to fit. This error has now been fixed, so if you order PCBs using my Gerber files, you won't have this problem. With all the components installed, the last thing to do was tin the exposed traces with plenty of solder. These traces carry hundreds of amps of current, so make sure you tin them with plenty of solder or you'll risk blowing up your induction heater. Ooh! How to make PCB life hack video. Hello and welcome back to another 5-minute crafts video. Today I'm going to be showing you how to make fresh PCBs from stuff you have lying around your house. Oh, I think they're ready. Let's check it out. Oh yeah, check out these straight out of the microwave. Oh, they're still hot. So it's really that simple, guys. You too can make PCBs at home using this method. Honest. And that's it. It's the last life hack video I'm ever watching. Unfortunately, making professional PCBs at home isn't easy, but with JLC PCB they make it so affordable that you don't have to. Starting from as little as $2 for 5 PCBs, they offer fast production time, a wide range of design options and colours to choose from. And they also offer SMD assembly, meaning your circuit boards can be delivered to your door ready to go right out of the box. Try out JLC PCB for your next PCB project. Now I moved on to making the induction coil. I've chosen to use copper tubing to construct my coil from. I've chosen this particular size of tubing as it will be easy to water cool should the need arise in the future. To make the coil, you can simply wrap the tubing around a cylinder such as a PVC pipe fitting. However, I 3D printed the spiral form, which should make the job a bit easier. As you bend the copper tubing, it work hardens, and the more you bend it, the harder it becomes. So here's a quick tip to soften the copper. Use a blowtorch and heat the copper up until it's just starting to glow red. Then quickly cool it in a bucket of water. This process is called annealing. After annealing, you'll find the copper is much softer and easier to bend, and you can repeat this process again if needed. My finished coil has 6.5 turns. The number of turns does affect the performance of the heater, so unless you know what you're doing, I'd recommend you stick with at least 6 turns on your coil. Also, it's important to have an air gap between each turn to prevent the coil from shorting on itself. Now I had to figure out how to attach the coil to the PCB. Alright, so now I've got my induction heater all assembled. Now we need to talk about how we're going to power it. Now normally when I'm powering a brand new circuit for the first time, I like to use my lab bench power supply back here. It allows me to set a low current limit so that in the event there's something wrong with the circuit, it doesn't blow up. But unfortunately, we're not going to be able to do that here. You see, this induction heater is self-resonating between the capacitor tank and the coil. And basically what that means is this needs a heap of current upon startup to start the oscillation process. So unfortunately, we're just going to have to hook it up and hope that everything works. If it doesn't, it's going to be spectacular. Now when it comes to power requirements, I'm looking for something that puts out between 12 and 40 volts DC, somewhere in that range, and can put out a lot of current in the order of like 50 to even 100 amps would be good. And that is something my little lab bench power supply cannot do. So I've come up with a rather Frankenstein of a power supply behind me. So I have this massive transformer. It takes the 220 volts AC wall power and drops it down to 28 volts AC, but at a lot of current. It's like 6 gauge cables coming out of the transformer. It's absolutely massive. That goes to a full bridge rectifier. You know who I'm referencing when I say that. This full bridge rectifier can handle up to 50 amps of current. And of course that needs to be smoothed out with a capacitor, and I've got a single capacitor, but it's huge. 34,000 microfarads up to 50 volts DC. And then of course this is where I can hook up my induction heater. But although the setup is capable of delivering the power that I want, it's not veritable anyway, it's a fixed voltage. And for testing, I want to see how far I can crank the voltage up. So to do that, I've got the whole setup plugged into a variac. So this takes the fixed voltage wall power and means that I can raise the voltage or lower it anywhere from 0 to 260 volts AC, which means I now have a power supply capable of delivering 50 amps of current at basically any voltage I need for this setup. Now you might be wondering to yourself, is this really my permanent power supply for the induction heater? No, it's not. This is just for testing different supply voltages and seeing how much performance I get out of the induction heater. Once I work out the sweet spot of where I want to run my induction heater at, I'll be buying like switch mode power supplies, which will be my more permanent power supply solution for my induction heater. But at the moment, we are ready to test, so let's get going. I connected my meter up to the input leads to measure the input voltage, and used my clamp meter to measure the input current. I'd recommend a minimum input voltage of 12 volts, which is where I chose to start. After powering up the heater, at idle it was drawing about 27 watts, which is pretty good. To test the heater, all I had to do was insert a piece of steel into the coil. Immediately you can see the power consumption increases. Even though the input power is set low, I could feel the pliers were getting hot to the touch. I checked the temperature of the heat sinks and they were barely warm, so everything is looking good. Before I crank up the power, first let's take a look at the power across the coil using my oscilloscope. Here we can observe a beautiful 50 kHz sine wave with a peak-to-peak voltage of 70 volts. We can also see how heating a piece of metal affects the frequency and voltage across the coil. So now we're ready to crank up the power. I used my DIY fume extractor as a fan to blow air over the heat sinks and caps to keep them cool. I wanted to increase the input voltage over several steps so I could monitor the temperature of the components to make sure nothing was overheating. You can see as the input voltage increases to 32 volts, the voltage across the coil rises to over 200 volts. And I think it goes without saying, but you shouldn't touch the coil while the heater is running. It's unlikely to severely shock you, but speaking from experience, it's similar to getting shocked from an electric fence, which is rather unpleasant. So yeah, don't touch it. Now I turned up the voltage to 48 volts input and played around heating different metal objects. Now at this point you're probably wondering if my induction heater will heat non-ferrous metals such as alloys, and so was I. So I grabbed an alloy rod and measured its starting temperature. After about 1 minute of heating I measured the temperature again and it had only risen by 1 degree, so this induction heater isn't suitable for heating metals such as aluminium. So to effectively heat non-ferrous metals such as alloy really requires two major things: a far more powerful induction heater, and also the frequency at which the coil resonates at plays a major role in efficiently heating non-ferrous metals. So really this induction heater is suited for heating ferrous metals only. Now when it comes to choosing a power supply voltage, I would recommend going with 48 volts as it yielded the highest performance, of course, efficiently heating metal in relatively short spaces of time. Now when it comes to how much current it's going to draw, well that's going to largely determine on the size of the metal that you're trying to heat. A smaller piece of metal in the coil will draw less power from the wall outlet. But I was able to draw a maximum of about 1.4 kilowatts from the wall. So that should give you some good idea of the kind of power supply you need. Now if you plan on building this induction heater for yourself and you're going to power it with more than say a kilowatt, I would recommend soldering some bare copper wire to the traces that connect the caps to the coil. When I was powering mine up with like 1.4 kilowatts, one of the traces began to melt the solder due to the high current, and when the solder dripped away it left the trace without any solder on top and it burnt out, and this resulted in a damaged MOSFET. So something needs to be done to improve how much current these traces can handle, and I think soldering some heavy gauge wire on top of the traces should avoid this happening to you. So I'm pretty happy with this project overall, and if you liked it, please give it a like. It would help the channel out, and if you want to see more builds like this, you know where that subscribe button is. Thanks to all my Patreon supporters, and I will see everyone on the next video. Bye for now.